So let's do the recap. First, we design a controller that comes with feedback term, robust term. Okay, and here's the open loop dynamics, and the control input tau is here. We design a label function, take the time derivative, right? Take the time derivative, and now you try to find the SS to substitute your controller, right? And the SS is mr dot, and that's in here. So this term gives you the access to substitute the control input tau. Okay, so you substitute the dynamics, and in E dot here, you need to observe what you should do with E dot. And in here, the better way is to use the filter tracking error to replace E dot by R minus alpha E. Okay, and then create the cross terms that can cancel out with another cross term. Okay, and it becomes clear and clear how you can design the robust term VR. Okay, cross term goes away, and now it's clear that what you should put in VR. Okay, and you need to, we regroup terms according to good terms and bad terms. Good terms are the terms that can make V dot to be negative definite. So here you only have R, so that's bad terms. You have plus something R squared, that's bad terms, but it can be combined with some minus R squared terms here, and this is good terms. Okay, so the two terms are combined, and as long as K is satisfied some condition, this term will be a good term, right? And here's another good terms that comes from here, and now you have only two terms to take care of. This is the one, and this is the second one. So you can now design, it's now clear, you can design VR and to deal with these bad terms. And the VR we design is K3C1 square R. Okay, because when you design this and use the completely the square, you can obtain this. Okay, doing some upper bound, you can obtain this. Okay, and this can be reduced by increasing K3. So increasing K3, you can reduce the tracking error. Okay. So this is where we were last time, and the result is EUB, because if you ignore these third terms, the two terms will be a negative definite. The term that can make V dot to be negative definite, right? But this is positive term, so it's EUB. Okay. Eventually, this term will prevent V dot, or prevent V goes to 0, okay? Because V dot eventually will be 0 before it get to the origin, okay? Any question here? If no question, now here's another controllers, and today I will give some of you the chance to write down the controller designs on board. Okay, so be aware, pay attention. Okay, anytime. And it doesn't mean that if you were here last week and you won't show up here. No, that's not the case. Okay, so everyone has the opportunities. So here's high frequency controller. Before it's high gain, now it's high frequency, which means the VR here will will eventually be designed as this, which have sine R. Okay, R is this filter tracking error. So I will just quickly go through the procedure, and you can recover some of the details based on the previous slides. Okay, so first we design the control high frequency controller. Second, open loop dynamics, and the third one is find the same level functions, take the time derivative, and you substitute the control input tau in here, which consists of a feedback term and high frequency term. So high frequency term here can combine with, multiply with this R that give you the absolute value of R. And that can be grouping with this bad term C1 absolute value of R. Okay, so as long as K3 is greater than C1, this term will be negative. Okay, and because it's negative, it can upper bound by 0 and can be dropped out, and this make V dot to be negative definite, which is really good, right? So you ensure that you can get a global asymptotic stability over global asymptotic tracking, because it's global because this is already unbounded. Okay, and it is asymptotic because it's negative definite. Okay, so if you implement these controllers to this kind of system, the kind of open loop dynamics, you will expect that the tracking error will go to 0. Okay, and in your simulation, you also need to not only plot out the tracking error, but also plot out the control input. Okay, and you can compare the difference between high gain and high frequency controllers. The control input will be very different. Okay, although the tracking error might both converge to 0, but the control input will be very different. Okay, so that's the summary is using high gain controller design as this. Okay, and basically they are feedback controllers, KR and plus K3C1 square R, and K3C1 square R is another, can be considered as another constant, positive constant, right? And stability is EUB, but high frequency is global asymptotic stability or tracking. Okay, and increasing K3 can decrease the EUB error. There's no upper bound. What you say is minus R VR. Yes. You substitute VR as K3 sine R, right?
Because sine R could be positive or negative.
Okay.
And K3 is always positive.
Right?
Yes.
And that's equal to minus K3. And these two terms can be combined as the value of R. And that's equal sign. Okay, because for sine R, and here is R, right? Do you agree with this?
Yes.
Right, okay, and what is R? R basically R, okay, R, okay, R, I put, so these two plots, right, different plots, 1, 2, and I put x-axis as R, okay, okay, you can put anything on the x-axis, y-axis is R and it's sine R, okay, and what's this plot? 1, 1, right? Right? 有没有问题? Take the product because you want R times sine R. Okay? You take the product. And R, right? So here's positive 1. here is R. Okay, so that's negative. So that's this. So no matter where R is, R sine R will be, and that's equal sign, there's no upper bound. Adaptive control. And again, for unknown systems, same dynamics over Lagrange systems. And we apply unknown constants. M and L are unknown constants. Okay, Q, Q dot are measurable. So let's first try the above function as 1 over 2 mr squared. Okay, and the open loop dynamics. Okay, here's the open loop dynamics. Okay, but because we are doing tracking control, which means that you want the tracking error to be 0. Okay, so I put filter tracking error as 0, R here, okay, rather than put Q here. If we put Q here, it's a regulation problem, right? So you put R here, and here's the new open loop dynamics, because, okay, here's Q dot dot, right? And here is R dot. But both are open loop dynamics because you haven't substituted your control input yet. E defined as Qd minus Q goes to 0 as t goes to infinity. And so we define a filter tracking error. Okay, and we so that is the open loop dynamics, right? And we need to find another open loop dynamics because that will be substituted into the V at Taylor time derivative. So we want to find what's V dot. Okay, and maybe you put put mr dot would be better. So mr dot base because there's another m in front of the Q double dot, right? So mr dot is, you take the time derivative on here, and where's the access for mq dot is in here, right? So you expand this qd double dot minus q double dot plus alpha e, okay? And here's the access control for control, right? Okay. So this is how that equation come from, okay? You substitute the control in minus mq double dot. Mq double dot is that. Okay. Plus m alpha e. Okay? 这样懂吗 ？And open loop dynamic is leg 1. Okay, 最上面那一个。Okay? Then in here you can see the control input tau over layer. And this is same as this second equation, the number 2 equation. Okay? Same as this. Okay? I think it should be minus here, right? Anyway. minus that, which is tau minus m g l sine q right, plus m alpha e, okay, and that is that, okay. Next, substitute this into the time derivative of v, okay. This can be replaced by the Orli's equation. Okay. Okay, ma. So now you want to regrouping terms, right? So you need to substitute what you design here, and I guess it's KR plus some terms. I have one more step here, okay? I have one more step here, but just neglect this for a moment. You jump to here. I design controller as some feedback control time plus some compensation term here, okay? And that's because we are using adaptive control, okay? But here we have feedback control terms, okay? And this term has different functionalities. So this term coming from, so this KR term times the R term here can create some good terms, which is minus KR squared, right? Okay? And that's essential to make V dot to be negative definite, because V is a function of R, okay? But you have other terms to be to cancel out, right? You have this, and this, right? You have three other terms to be canceled by some term you design here, and these are unknown, okay? So you cannot design some known term, some unknown term here to cancel these unknown terms, okay? That doesn't happen, okay? So what I will do here is adaptive control, okay? And the interpretation here for theta, the y here, in other words, this term have something to do with these three terms, right? And that's right. And the relation is, if I write this down, if you take a look on these three terms, you see here's unknown, right? Empty, sorry. Here's unknown. Here's known. Unknown. Unknown. Known, right? Unknown. Known, right? So they are structured as unknown times known. Okay, so this is how this y theta come into play. Okay, in y theta, y is the known terms, theta is the unknown terms. Okay, and you multiply. So y theta basically is the summation of these three terms. 能懂吗? So the way we do it is you have m here, you have m here, right? So I combine the two. I say m times mq double dot times mg mlg psi q plus m alpha e dot. I combine these two, okay? So it's equal to m q qd double dot plus alpha e dot plus m l g psi q. Okay, so these unknown terms is unknown terms. Right. Now you can write, you can do it as a matrix form, which is you put two vectors multiplied the product of two vectors. And according to this, we put unknown term here, m and ml. And m times what? Times these terms. Okay, times these terms. ml times these terms. Okay. 听懂啊? So let this is what it is here. Okay. So you can put all this stuff, this summation of these three stuff as y theta. Okay. So we can narrow down to plus y theta, right? And you have torque here. You have torque here. So, right? I haven't used torque yet, but just condense these three terms into one terms, okay? And control. So in my control, it's clear now that I can use, R here, okay? So I can design feedback term to create negative definite terms and some terms which is known, right? Y is known, and times some estimate of these unknown terms, okay? That give me minus kr squared plus what? Plus the difference of these two terms, right? So that's ry theta minus theta hat, okay? Okay. So that give me minus kr squared plus ry so here's y transpose, okay? Y and theta are column vectors, so y transpose will be row vectors, okay? So the product of these three is y transpose theta, okay? So here's a typo here, it should be y transpose theta, y transpose theta hat, okay? So y transpose theta tilde defined as theta minus theta hat. Okay, the estimate error. What can you do? We design VS function. It's a PD. Okay, it's a function of R, you got a v dot that is minus kr squared, but another term here cannot be cancelled, right? We get stuck here. So, but you can do better, okay? So let's do it another way, which is the next page. So the difference is cannot be cancelled, okay? So next we modify the liberal function as this, okay? We add another terms. Let's call, okay? And we want to show that v will eventually goes to 0. And that means this r will be 0, theta tilde will be 0. Okay. 这个看得懂吗? And this is some constant matrix. Okay, and this is a column vector, row vector, okay, because it's transpose row vector. This is a 2 by 2 matrix. Okay. It's a quadratic form. Okay, this is quadratic form. Okay, and x is x1, x2. Q is belong to R2. Okay, and Q is a matrix called Q1, Q2, Q3, Q4. It's 2 by 2. Okay, so this implies x1 times x1, x2, Q1, Q2, Q3, Q4, x1, x2. So when you multiply this, you will get some stuff. But usually we design that gamma as a diagonal matrix, which is it will be 0 only off diagonal terms. Okay, so this gives you a simpler form, which is Q1 x1 squared plus Q4 x2 squared. So it's quadratic form. Okay, 看懂吗? So it's positive definite for that, for this. Okay. So this is a diagonal matrix. Okay, positive diagonal matrix. A positive diagonal matrix. Okay. So you add this term, you take the time derivative. Okay. That gives you theta tilde t 好玩的吗? Theta tilde t, and this is constant, and this is dot. Okay, and 1/2 will go away because it's squared. Okay, it's quadratic. Okay, and because this is constant, right? When you take the time derivative, this will be 0. This is a function of time, so it will be 0 minus dot. Okay, and sorry, I should put theta t. Okay. This gives you theta tilde t and minus theta hat. Okay, here's hat. Okay, and this term is helpful because you will see in a minute. So this term will come into here as well as here, right? Okay. Now you want to cancel. You want to use this term to cancel this term out. Okay. So there's a chance you have this term. You have this term here. Okay. Although one is transpose, one is not, but that's fine. You can design theta theta as gamma. Okay, gamma, cancel this gamma, minus 1 out. And you can put y here and r here. Okay, y r transpose. Okay, if you design theta hat as this, you substitute into here, you will get minus kr squared. Okay. And you are almost done. So here, is it a negative definite? Yes or no? Yes or no? Raise your hand if yes. If no, raise your hand. No, because you add one more term here, right? So it's negative semi-definite. But you can use Barbara's lemma to show R goes to 0. Okay, and because we are running out of time, there will be the next, will be on next week. So this is how we design the adaptive law. Okay, so it's a function of time. It's a function of time. That means so what you do here is you design a controller as this. Right? You design these controllers. Feedback term, fine. And here you have y theta hat. And theta hat is the estimate of this true theta, right? And because it's estimate, you need to learn how theta hat can approximate theta. And the learning algorithm is this. Okay, this theta follows the dynamics. Theta hat is equal to gamma, which is the control gain, y r transpose. Okay. R transpose 有没有写错？R transpose 我是不是写错了？应该没有 ，y theta 没有啊，就是 r 而已啊。R is a scalar, so just r, okay? Just r. R is a scalar. Okay. Let's see. Okay. So why they will be cancelled out? Because, okay, let's try this. Were it equal to theta tilde gamma minus 1 and this, right? Okay, and this cancels out. So that gives you are they equal? This equal to this? 有一样吗？好像没有，对不对？ And maybe I should ask you one more question. Is this product a scalar? Is it a scalar or a vector? The product? Scalar, right? Everything in the above function is scalar. So it's a scalar, right? So you take the scalar, the transpose of scalar is equal to itself, right? So if you take the transpose, it should be still equal, right? You take the transpose, this gives you R. Okay, you take the transpose, RT, YT and theta tilde. Okay, so it's the same. So they can be cancelled out. Okay. And we have some other work to do, but there will be next time. Okay. Any question here? But it's an SD, right? But we only trying to show that R converges to 0, but not this. Okay. Theta tilde, which is the difference between true parameter and the estimate, is not necessarily going to be 0. Okay, it's not necessary. So even that you find the tricking error goes to 0, but it doesn't mean your the estimate will approximate the true value. It's not necessary. Okay. Because there are some problems that prevent it converge to the true parameter.